Welcome, everyone. Today, we're going to talk about the pixel paradox. We'll explore why naive visual memory fails in GUI agents and make the case for a new approach called action-grounded cropping. This presentation is based on a failure mode study of modern GUI agents using the 2026 OSWorld benchmark data. Let's start with a hard truth. The frontier of GUI automation currently relies heavily on full-screen visual memory, and this is a mistake. Recent advances feed frontier models, like GPT 5.4 Mini, Claude, and Gemini, massive logs of past decision trajectories and full monolithic screenshots. But there's a fatal flaw here. Consuming these monolithic images lacks an explicit representation of the local regions that actually determine actions. As a result, modern GUI agents continue to fail in non-trivial, highly structured ways, and as you can see from our chart, performance eventually hits a warning wall. We need to dissect exactly why this happens. To understand this, let's look at the anatomy of agent failure across the pipeline of perception, reasoning, and action. We've identified 4 main breakdowns. First is visual state misunderstanding, a perception error where the agent misreads the visible screen. Second is cognitive failure, a reasoning error where the agent misunderstands the task or plan. Then we have action stage errors, hidden operation blindness, where the agent misses invisible UI layers, and grounding error, which is a mechanical clicking failure. We often assume that by prep-ending full screenshots, we are fixing perception, but the reality is much more complex. Let's dive into an autopsy of these failures, starting with breakdowns in logic and state. In this first example using LibreOffice Impress, the model experiences a cognitive failure. It executes a fundamentally wrong subtask plan by trying to click a slide thumbnail instead of opening the background settings. In the second example using LibreOffice Calc, we see a visual state misunderstanding. The agent is supposed to fill the total earned cell, but it misreads the visible screen layout, confusing one cell for another and writing in the total hours column instead. Moving on to part 2 of our autopsy, let's examine breakdowns in action and execution. Look at this GIMP example on the left. The agent's intended target and action are perfectly correct. It wants to click close tab, but it makes a grounding error because its mechanical coordinate clicks slightly off target. On the right, in a web browser, we see hidden operation blindness. The agent doesn't directly see an add folder option on screen, so it attempts to trigger an invisible operation using a keyboard shortcut, but it triggers the wrong one by pressing Ctrl plus Shift plus B. This brings us to the invisible UI and why full screenshots fail. Think of it like an iceberg. The visible UI, like buttons and text fields, is just the tip. Below the surface are hidden operations, keyboard shortcuts, right-click context menus, and overflow options. The iceberg problem is that modern OS navigation requires operations that aren't explicitly drawn in pixels until prompted. When we feed an agent a full 1080p screenshot, the noise of the visible UI actually distracts it from reasoning about these crucial, context-dependent hidden actions. Furthermore, there's a significant gap between perception and mechanics. Grounding error proves that simply recognizing a target is not the same as physically touching it. Even when visual memory helps the agent form the perfect plan and identify the exact UI element, monolithic image processing degrades coordinate precision. Essentially, the agent knows exactly what to click, but it forgets where the bounding box ends, missing the mark by just a few pixels. We can map these issues on what we call the agent diagnostic matrix. On the y-axis we have state-level versus action-level failures, and on the x-axis, contextual/logical versus visual/mechanical errors. This creates 4 quadrants: cognitive failure and hidden operation blindness on the logical side, and visual state misunderstanding and grounding error on the visual and mechanical side. This leads us directly to the pixel paradox, which is essentially a zero-sum game. Our empirical testing on OSWorld with GPT 5.4 Mini reveals a startling trade-off when agents use full image screenshots for memory. The benefit is that it reduces state-level failures. For instance, visual state misunderstanding drops from 73.1% to 69.6%. But the cost is that it simultaneously worsens action-level failures, increasing hidden operation blindness by 11.7%. The core insight here is that crowding the agent's context with task-irrelevant background pixels introduces noise that destroys action precision. The solution lies in understanding that the geography of action is highly local. GUI control is rarely determined by the entire screen. Instead, it is governed by intensely local visual states that recur across tasks. Right now, we are forcing vision language models to read an entire map just to find a single street. To fix agentic memory, we don't need smarter models. We need to hand the model a magnifying glass. That is why we are introducing action-grounded visual memory, or AGMem. AGMem is an information compacting framework that completely abandons the monolithic screenshot. Instead, it stores only image crops that capture the exact local GUI region closely related to a successful action or a recovery. Our philosophy is simple: which pixels are stored matters just as much as whether memory is used at all. Here is how AGMem distills signal from noise. It employs a domain-compacting retrieval system. At test time, instead of wading through massive, noisy full-screen trajectories, the agent retrieves only relevant crop view memories and uses them during planning. This automatic pipeline provides decision-critical visual evidence while completely avoiding the token cost and distraction of repeatedly processing full-screen images. In a direct memory architecture showdown, the differences are stark. Full image memory uses 100% monolithic screenshots, resulting in high noise and redundant computing, which actually exacerbates hidden operation blindness by 11.7%. AGMem, on the other hand, uses local-focused crops. This provides highly action-dense signal, mitigates hidden operation blindness, and ensures highly compact token usage. The empirical impact of this focused lens is undeniable. Looking at our data highlights from the 2026 OSWorld benchmark using GPT 5.4 Mini, AGMem achieved a 33.3% increase in overall task success rate over the full image baseline. More impressively, it drove a 37.3 percentage point reduction in visual state misunderstanding and a 26.3 percentage point reduction in hidden operation blindness. By simply restricting visual memory to the geography of action, the agent's logical and mechanical errors plummeted. In conclusion, we need to stop feeding agents the noise. As GUI agents scale to complex operating systems, adding more pixel data does not equate to adding more context. The future of workflow automation isn't about giving agents bigger eyes. It's about teaching them exactly where to look. Action-grounded visual memory ensures that when agents look to the past, they only see the signal. Thank you for watching.